In rigorous mathematics, a circle is defined by a single, unwavering rule. It is a shape that exists only because of a specific geometric condition. This is a locus, a path formed by a set of points that all maintain a perfectly fixed distance from one central anchor. This definition allowed the mathematician Āryabhaṭa to calculate pi to 4 decimal places in 499 CE. By treating the circle as a collection of fixed distances, he provided a value of 3.1416 centuries before modern computers. To see how this geometry functions, place any straight line, a chord, between 2 points on that boundary. Then connect those endpoints back to the center. Because all radii are equal, these two center lines are identical in length. This means that every chord in a circle naturally forms the base of an isosceles triangle. This hidden triangle is the starting point for almost every geometric proof. It is the engine that drives the more complex rules of the system. When we drop a perpendicular line from the center to a chord, it bisects it. Because our internal triangle is isosceles, that vertical line must cut the base into 2 perfectly equal halves. This logic scales up into Theorem 9. By splitting the inscribed angle into 2 smaller isosceles triangles, we find their exterior center angles are twice their interior counterparts. Combined, the central angle is exactly double the boundary angle. No matter where this inscribed angle moves along the arc, it remains exactly half. This mathematical constancy is unique to circles. Engineers rely on it to ensure that load distribution remains perfectly balanced across circular structures. We can expand these rules to 4-sided shapes. When this polygon sits so that all 4 corners touch the boundary of a circle, it is called a cyclic quadrilateral. These shapes follow a strict law. Their opposite interior angles will always sum to exactly 180 degrees. In 628 CE, Brahmagupta used properties of concyclic points to develop formulas for the circumradius, connecting the sides of any triangle to the circle that surrounds it. This geometry is visible in the rotational symmetry of traditional Rangoli patterns. Each sector is created by using equal central angles to produce identical arcs across the design. Ancient mathematicians and artists used these theorems as practical tools to bring order and measurement to the physical world. Now let's see if you can apply these core rules yourself. First, the definition. What is a circle in precise geometric terms? It is a locus of points maintained at a fixed distance from a center. Next, a calculation. If the central angle here is 110 degrees, what is the value of the angle hitting the boundary? Based on Theorem 9, it is exactly half, 55 degrees. Finally, the logic. Is the fact that every chord forms an isosceles triangle the reason why a center line bisecting a chord forms a 90-degree angle? Yes, the symmetry of that triangle makes the perpendicular intersection inevitable. Mastering these deductions is the first step required before handling real-world engineering problems. Consider an archaeologist who finds a broken fragment of a stone wheel. To reconstruct it, they must find the original, mathematically perfect center. We start by drawing 2 straight chords across the curve of the fragment. We then apply the theorem of perpendicular bisectors, drawing a 90-degree line from the exact midpoint of each chord. The intersection point is the wheel's original center. Here is a final problem. Is it possible to design a perfectly rectangular window frame to fit inside a circular wall opening? Yes. Because rectangles have 90-degree corners, their opposite angles sum to 180. This satisfies the condition for a cyclic quadrilateral, allowing it to fit the circle perfectly. By following the rule of fixed distance, you can identify the internal symmetry of any circular form. Practice these skills and continue the study of geometry at edunotch.in.